Hello, everyone. If you haven't already, just say hello in the chat. Maybe tell us what the weather's like where you are. It's rather rainy and windy over here. We'll be starting in just another minute. "75 and sunny." Oh, I'm jealous.
Phoenix is always a bit like that until it gets really hot. Then it'll be like 120 degrees.
Oh, okay. Oh, wow. Tornado warnings. Okay. All right. Okay. So we'll get started. Last time we were talking about transformers, so I'll just wrap up. I'll answer a question I think that Katie had last time about that, and then we'll move on to inductors. So very briefly, if you'll remember, the structure of the transformer was we had a primary coil, and it was wound around a transformer core, which was basically a material that magnetic field lines prefer to travel through. And then we had a secondary coil with typically a different number of turns wrapped around it. So this was the primary, and this was the secondary. And so if we ran an AC current through the primary, the current would generate a magnetic field, and those magnetic field lines would travel through the core, and so the secondary coil would see them. And because it was an AC current, the current was constantly changing, so the field was constantly changing. So the flux that the secondary coil saw was also changing constantly. As a result, by Faraday's law, there would be an induced EMF over here. And so if this was connected to, say, a resistor, then we would have an AC current flowing here through the secondary coil. I'll draw the... So by the way, this symbol is an AC voltage source. So it's a little sine wave indicating that it's AC. All right. All right. And so there was a question about the flux and how it ended up that even though that each individual turn of the coil here and each individual turn of the coil here saw the same flux, how did they end up with different voltages? So the idea is that, so once there's a current flowing through here, then that produces its own flux, and so they start interacting with each other. And this type of interaction between two coils by virtue of the flux and the changing flux in Faraday's law, this is called mutual inductance. And the idea is, so we know that by Faraday's law, EMF is equal to the negative of the rate of change of magnetic flux. And I'm putting a total here because, for example, for the secondary coil, the EMF induced in that is going to be related to the rate of change of the total flux that it sees. All right. Now, what do I mean by total flux? Well, because there are a certain number of turns here, right? Each turn is acting like more area, right? And so it's essentially multiplying the effective flux. Okay, so I could write this out as E secondary is equal to minus NS All right, so what I'm saying is that the total flux seen by the secondary coil is the flux seen by a single turn times the number of turns in the secondary coil. Okay, And a similar relation should hold for the primary coil. So we would have E primary is equal to minus N primary d phi b dt, where this is again the flux, the rate of change of flux through a single turn. Okay, but if we look at what's going on over here, the field lines, let me use a different color, the field lines are just wrapping around like this. And so the flux seen by a single turn over here is the same as the flux seen by a single turn over here. So I can equate d phi b single turn over here to the same thing over here. So what does that give me? Well, I can solve for this. I get the voltage across the secondary coil divided by the number of turns in the secondary coil. And there's a minus sign, which we forget about. And similarly over here. And so that is how we end up with the transformer equation, V secondary over V primary. Well, actually, let me write it the other way. V secondary over N secondary is equal to V primary over N primary. And then if we want, we can rearrange that to V secondary over V primary is equal to N secondary over N primary. Questions?
Yeah. The end is the number of turns divided by the, wait, no, that's little n. Big N is just the number of turns.
Exactly, yeah. Big N is just the number of turns. Little n is number of turns per unit length. Other questions? Okay.
I have a
Oh, yeah.
question. That's not about transformers, but I was just curious if during this class we're gonna go over what the midterm is gonna look like in this distance thing.
Well, I can tell you that it will cover up till the end of chapter 28, right? So before Faraday's law, like basically everything up to like Ampere's law, including Ampere's law. As for what it's going to look like,
Or when is it?
well, hopefully we'll stick to the schedule and aim for Thursday. And it'll probably be basically a take-home exam. It will be a scaled-up version of the quizzes we've been trying for the last few weeks. Dr. Both and I still need to iron out the details, so that's why I can't give you a definitive answer. But
Okay.
that is most likely what it's going to be. It's just going to be a scaled-up take-home exam. We'll give you several. I mean, like, obviously, since the original midterm was like 90 minutes, and we'll just scale that up by a much larger factor. And so you'll have several hours, just complete the exam when you can, and then scan and upload.
Sounds good.
All right. Other questions?
It's on Thursday, right?
Hopefully on Thursday, yes. And of course, no homework this week.
Will it still be a 90-minute exam?
As in, well,
minutes to complete, but like we'll just have a certain amount of time to complete it and upload it.
Basically, yeah. I mean, hopefully a little less than 90 minutes, more like an hour 10. Is you should be able to finish it in that time. But yeah, we'll just give you lots of buffer time to allow for, yeah. All right. Okay, so that pretty much wraps up transformers. I'll just end one more time with the most relevant equations. So we have V secondary over V primary is equal to N secondary over N primary. And what we said was that power secondary would be equal to power primary. because energy is conserved. And so because of that, the current would go inversely compared to the voltage. So this would be I primary over I secondary. So when the secondary voltage is higher than the primary voltage, the secondary current will be lower than the primary current. Okay, so
they're directly proportional. Like you don't need to have any kind of like a like value to multiply up or anything.
For an ideal transformer, yeah, these are strict equalities. In real transformers, of course, there will be some loss along the way, so there will be some numerical factor in front, but that's individual to each transformer. So,
okay.
All right. So, just like capacitors were what we would basically use if we wanted a nice uniform electric field, and we use them as energy storage in circuits, there is a similar device called an inductor that does the same thing for magnetic fields. And well, how do we produce a nice uniform magnetic field? We use a solenoid. So most inductors are in fact just solenoids. All right, so what are a few properties that we can talk about? So for a capacitor, all right, yeah, I'll start up a sort of comparison, maybe. All right, for a capacitor, we had as one of the fundamental relations was Q is equal to C delta V. For an inductor, often what we'll talk about is the magnetic flux is equal to yes, L times I. This L here is the symbol for self-inductance.
Is self-inductance like what we've talked about, how like it goes in the other direction when you have like a change in?
Pretty much, yeah. So the idea here is that when you pass a current through this coil, it generates a magnetic field. But now if this current starts changing, then well, each turn here is seeing a magnetic flux. And so if that starts changing, it will create an EMF that tries to resist the change. So an inductor's, you could say, the way it thinks, or its motivation is that it will do what it can to prevent the current running through it from changing. So if your current suddenly starts decreasing, then the inductor will start acting like a battery and drive current in the same direction. If your current starts increasing, it will try and oppose that and act like a battery in the opposite direction and try and decrease the amount of current. So we'll see, just like we looked at RC circuits, we're going to look at RL circuits. But first, just a few general things about the inductor. So let's try and get an expression for this inductance, self-inductance. So for a capacitor, we had capacitance. For a parallel plate capacitor, we showed was epsilon naught A over D. So it was purely geometric. It depended only on the area of the plates, the distance between them, and then epsilon naught was a kind of universal constant. So the same idea applies over here. So let's try and figure out what we have over here. So to calculate the flux seen by this coil, well, it's a solenoid. So we know that for a solenoid, the magnetic field is mu naught Ni. And so then it's nice and uniform. So then to get the flux through a single turn, we just need to multiply that by the area of a single turn. So that would be pi r squared. All right, but then there are, of course, many turns. So the total flux would be big N times mu naught Ni pi r squared. And often what we do is we rewrite this. So we have mu naught I pi r squared. And then what I do is I rewrite big N as little n times the length. So try and be careful. In Flip It, I think they called it Z. Here I'm using a little l to avoid confusion with capital L, which is self-inductance. So this combination would be big N, and then we still have one more little n there, so it would be n squared, like that. Okay, so if this is the total flux, and we have the formula phi b equals Li, then everything except I is going to be the inductance. So we have the inductance for a solenoid is mu naught pi r squared little n squared little l. And we can see that, yeah, just like with the capacitor, it's purely geometric. It depends on the radius of the solenoid, depends on the length of the solenoid, depends on the number of turns per unit length of the solenoid. Questions?
So is L for sort of like in the equivalence of C?
Mm-hmm. So it's a property of an inductor, yeah. So for example, the capacitance was a measure of how good a capacitor was at storing charge, right? It's basically Q over delta V, right? So for a given delta V, how much Q can you cram in? An inductor is, well, since it's related to rate of change of current, what we end up seeing, okay, I'll just switch over to another page. So we have phi b, whoops, is equal to Li, but we know that EMF is minus d phi b dt, and so that becomes, because L is purely geometrical, it doesn't change with time, and so we can pull that out. So we have minus L di over dt. So this is sometimes called the back EMF, because as I mentioned, if di over dt is positive, right, if your current is increasing, then this acts like a negative EMF. So it's an EMF trying to oppose that current and decrease it. So yeah, so this is back EMF. And the L here is a measure of how good it is at opposing that change in current. The bigger L is, the bigger the back EMF is. All right. Let's see. Right. So just like we could talk about energy stored in a capacitor, we can do the same for an inductor. So for a capacitor, we had three different formulas. So we said it was 1/2 Q squared over C. We said it was 1/2 C delta V squared. We said it was 1/2 Q delta V. So similarly for an inductor, the most common one we use is it is 1/2 Li squared. But remember that we can also use that relation phi b is equal to Li, and so we could express this in terms of the flux, and either the flux in the current or the flux in the inductance. But since usually current is much easier to measure than flux, we usually just use this form.
This is like potential energy?
Yeah, this is like potential energy. So basically the idea is that because an inductor resists a change in current, if you want to ramp up from zero current to a final current I, you need to do some work, and that stores potential energy in the magnetic field in the inductor. And that's this much of potential energy. Okay, so just like we talked about RC circuits, let's take a look at an RL circuit. But to do that, well, we need to know what the Kirchhoff rule is for an inductor. And so the rule is, so the circuit symbol for an inductor is just springy symbol like that. And so the idea is that if you have a current flowing through an inductor, and you cross the inductor with the current, then the term that you add is minus L di over dt. Right? If you cross an inductor going against the current, then it will be plus L di over dt. So in that way, it's a little like a resistor in that it depends upon whether you're going with the current or against the current when you cross. All right, let's see that in action. So we'll look at the simplest possible RL circuit. We have a battery, a switch, an inductor, and a resistor. All right, so this is L, this is R, this is E. All right, so at t equals 0, switch is closed. And so then once the switch is closed, I'll just draw it closed in a different color. Once it's closed, let's do the loop rule. So I'll start over here. I cross the battery. I'm going from negative to positive, so I'm going to gain E. I cross the inductor, and I'm heading with the current. So once the switch is closed, we'll have a current I flowing around clockwise. So I'm going with the current, so I'll have minus L di over dt. Then I go with the current across the resistor, so I have minus IR, and I've reached back to the starting point, so this is equal to 0. All right, so we know that the current will change with time, and so we want to figure out how it changes with time. So I'm going to solve for di over dt. So just moving things around, I have E minus IR over L is equal to di over dt. And so if I want to find the current as a function of time, I need to get all the current terms on one side and time terms on the other side, and then the variables will be separated so I can integrate them. So let me do that. So I'll have, let's see, yes, dt over L is equal to di over E minus IR. But to make this side easier to integrate, I want to, I don't want it to be IR, I don't want it to be just I. So I'm going to pull out a factor of minus R. So I get di over minus R, and here I'll have minus E over R plus I. Right, you can see that if I distribute this, it'll come back to this form. All right, I'll move the minus R over, and so then I have minus R over L times dt is equal to di over I minus E over R. And now I am ready to integrate. Any questions so far? Oh, Katie, yes.
I'm just wondering, like, earlier when you talked about the big N and the small n, I'm just a little confused about that.
Okay. So big N is the number of turns. Little n, so let me just write it over here. So big N is number of turns. And little n is big N over the length of, say, the solenoid. So it's the number of turns per unit length. Right? So big N is just a pure number. Little n is, since it's a number of turns per unit length, it's measured in like turns per centimeter or turns per meter.
How do you measure turns?
Just in like 1 turn, 2 turns, 3 turns. So it's usually integer counting.
Oh, so it doesn't have a unit.
No, no.
Okay, thank you.
All right, so we've reached this relation. So let's integrate both sides. So here the variable of integration is t. So I'll go from 0 to some time t. And on this side, the variable of integration is the current, I. And we know that initially there was no current, right? Initially the switch was open and then we closed it. But before we closed the switch, there was no current. So it starts out from a no current state, starts out from 0. And we're trying to find some I at the time t. It's getting a little dark here. Let me just hold on 1 second. Let's plug in. All right. A little bit better. All right. So this side, R and L are constant, so I just get T and evaluated at T and 0. So that would be just minus RT over L. On this side, I have DI over this, so it's going to be a natural log. So I'll have natural log of I of t minus E over r minus natural log, and now the I has gone away, so I'll just have minus E over r. I can rewrite the right-hand side to a fraction. So I have that. This side is still just minus RT over L. But to make life a little bit nicer, I'll write that as minus T over tau. Right, so tau, just like with the RC circuit, is the time constant. So tau, if we compare, we can see that tau is L over R.
Wait, what are you rewriting? Oh, the R, negative R. So negative R over L is tau, or just R over L?
L over R is tau. So if I'm dividing by tau, then the minus sign is still there in both terms. So yeah, it just flips over since I'm dividing by a fraction. So
L over R.
sorry, yeah.
Will you pull it down just a little bit? I'm sorry. There you go. Okay.
All right, so let me turn the page and follow up on that. So I have minus t over tau is equal to natural log I minus e over r divided by minus e over r. And to get rid of the natural log, I need to exponentiate both sides. So I can do that. I can rearrange stuff. And so finally, what do I get? I get I of t is equal to e over r times 1 minus e to the minus t over tau. All right, this is a very familiar form. And so we see that, oh, okay, when I turn on the switch, what I see is that I get this exponential decaying upwards, if you like. So it has this curve and it asymptotes finally to a steady current value.
Heat. How did you get from this step to this?
Okay, yeah, no, I did skip a little bit. So I exponentiated both sides, so I get e to the minus t over tau is equal to just this fraction.
Mm-hmm.
And then I just solve for I. So I multiplied.
Oh, okay.
All right. Now, but remember, one word of caution, remember that this was just for the simplest possible RL circuit. So it's not always going to be E over R out here, right? Just like for the RC circuit, the capacitor doesn't always charge up to the voltage of the battery. It's whatever voltage you can get, which is not necessarily the full voltage of the battery. So similarly here, it might not be the full voltage of the battery over here. So we'll just keep it general, and we'll say I of t is some I final times that. Okay, so this is more general and thus more generally applicable. And this is what you might call a charging inductor. Charging is sort of the wrong word because it doesn't really store any charge, it's just a current. But it's when the current through the inductor is rising.
So then, what would be your general term for tau? It would be like.
So tau, we said was L over R. So this would be basically L effective over R effective. As seen by the R effective as seen by the inductor. Let me clarify that. So as in, if you took out the inductor and stretched out the circuit, what is the, and like left the open space for the inductor, what resistance does the inductor see? That is the R effect. So this will maybe be a little clearer once we do a few examples, but yeah, this is the general
How
form.
effective would be like if there are multiple L's?
Exactly, yeah. All right. So this is for the charging inductor, and so we can visualize a case where there would be a discharging inductor as well. So a slightly different circuit. So let's see. Yeah, okay. So we'll have a switch and two possibilities. Let's see. Right. And so we have the inductor and resistor.
Can you move it up a little bit?
Sorry. Yes, absolutely. Inductor and resistor over here. And let's see. We'll have a battery and resistor over here. Okay, so R2L. All right, and say this is switch position A and B. So you can see that when the switch is in position A, then the circuit is, okay, we have battery, inductor, and resistor R1. So it'll be charging up then. And then we can flip it to position B. And now the battery is no longer part of the circuit. And but remember that the inductor doesn't like the current to change. So it will fight to keep the current going. It will act like a battery itself, and it will continue driving a current. And now if the switch is in position B, then it will have a loop that it can follow through R2 over here. So this would be a case of a discharging inductor. So A is charging and B is discharging. And I'm not going to go through the whole derivation again, but unsurprisingly, what we find is that the current, I mean, the inductor fights, but it can't win the battle. And what we find is that the current will decay exponentially according to this relation.
Is tau still the same?
Well, in this circuit, it would not.
Right, but it's still like.
Oh yeah, it's still L over R, yeah. Questions?
So is the tau gonna change because it sees different resistances?
Yep.
Or no?
The charging time constant will be different from the discharging time constant in this case. Yeah.
Is there different resistors?
Yeah. All right. So I'll go through an example problem. And just like the capacitor had limiting behaviors, right? We knew that if it was a completely uncharged capacitor, we could treat it like a plain wire. If it was a fully charged capacitor, we could treat it like a broken wire. There are similar limiting behaviors that we can do with the inductor. So I'll go through an example problem and then we'll try some. So let me share screen. What's going on? Ah, there. That, share, and full screen. Okay. Just have the laser pointer. Okay, so that was the transformer. We've talked about that. All right, so here's our sample circuit. We have the simplest kind, battery, resistor, inductor. The units of inductance are henries. So that's why the capital H over here. All right, so first question is, just after the switch is closed, what is the current through the battery? So remember that the inductor doesn't like the current running through it to change suddenly. So since before the switch was closed, the current was 0, it's going to keep it at 0 for just a fraction of a second. And then it's going to climb, it's going to lose the battle. But at t equals 0, just after the switch is closed, the current is 0. All right. Just after the switch is closed, what is the rate of change of current through the inductor? Okay, so let me just sort of illustrate that. So what we're talking about here is if I was plotting current versus time, we've said already that it would follow a curve like this. And so we're basically asking, what is the slope at this moment at t equals 0, right? What is di over dt at the initial moment? Question?
No, I'm just thinking about it.
Okay.
Sorry.
All right. So let's figure that out. So for that, we do a loop rule. So I'll go around. So we'll first cross the battery. So okay, first let me write it in symbols. So we have E, then we cross the inductor in the direction of the current. So I have minus L di over dt. And then I cross the resistor. So I have minus IR. Should be a little serif over there. All right, is equal to 0. And we know all the values. We know that E is 12. We know that L is 4 henries. We know that the current initially at t equals 0 is 0, so this term just drops out. So I can solve for the di over dt, and I just get E over L, which would give me 12 over 4. So that gives me 3 amperes per second. Right. So, so yeah, that would be the rate of change of current.
As soon as the current isn't zero anymore, that will change.
Yeah, this is continuously changing. That's true. All right, and then a long time after the switch is closed, what is the current through the battery? So a long time afterward, since there hasn't been any sudden change, right, everything has become steady. And so if there's no change, then this is essentially just a long wire, right? So a long time afterward, once the current is steady, the inductor can be treated just like a plain wire. And so if it's a plain wire, then the battery just sees 6 ohms over here. And so we see that it's 2 amps is the current through the battery. And a long time after, what is the rate of change? Well, it's 0 because everything has become steady.
I have a question about like, when is the inductor going against the current?
When is the inductor going against the current? Oh, initially, right after the switch is closed, right? The battery wants current to start flowing immediately. The inductor fights against that. So yeah, actually, if we try to do a loop rule, this is the loop rule at t equals 0. If we think about what's happening, the battery is giving us 12 volts, and then we're losing it all across the inductor and nothing across the resistor because there's no current at that moment. So the inductor is acting like a battery almost, but pointing in the opposite direction. So you would gain 12 volts over here and then lose 12 volts over here.
Okay.
But then as time passes, it's like this battery voltage is decreasing. So it's losing less and less, and the resistor is accounting for more and more.
Okay, thank you.
Mm-hmm.
So it's being given off as power at the beginning?
Say again?
It's being given off as power at the beginning?
What is being given off?
The inductor, like, it has to do something with the current, right? So it's just giving it off as power?
Oh, well, I mean, at t equals 0, there's no current. So in a sense, there's no power there either. But then as time passes, say again?
Like, what's literally happening to the electrons as they're moving for there to be no current?
Well, I mean, there's no current, so they aren't moving. I mean, it gets, of course, a little bit more complicated than that. But basically, yeah, the inductor responds to, when we close the switch, the electric field spreads from the battery. And so the coils in here respond to that changing electric field and create, and that they create an EMF in the opposite direction.
Okay.
Okay, so let's look at a problem. Okay, so I was just walking through the previous one. All right, so here is our first problem. And let me pull up a poll. This is question 6. Yep. Question 6. And launch poll. So the question is, just after the switch is closed, this is a slightly more complicated circuit, right? Just after the switch is closed, what is the current through the battery? Okay. So, all right, there was a clear winner there. There were votes for other options. So what's going on? So we just closed the switch. Initially, the current through the inductor is 0, so it wants to keep it at 0. So it will act like a broken wire, right? So no current will flow through here at t equals 0. Hold on, I forgot that you couldn't see my mouse. All right, no current will flow through here at t equals 0, but there is current flowing through here because there is a loop. And so we'll see the current from the battery will see 6 ohms plus 6 ohms, 12 ohms. So you're 12 volts, 12 ohms, you get 1 ampere of current initially. All right.
Okay, wait, I'm confused. So the current flowing through the inductor is 0, but the current flowing through the battery isn't 0.
That is correct.
Okay.
All right. So what is the rate of change of the current through the inductor? Yes. So let's poll again. Okay. All right. Clear winner for C, 2 amperes per second. And that is right. So if we remember, this is just after the switch is closed. So we've already established that there is 1 ampere of current running through here, right? So if I do a loop rule, say I can either do this outer loop or I can do this small loop over here. If I do the outer loop, I get plus 12 minus L di dt minus 6 times 1, right? Because 6 ohms, 1 amp current is equal to 0. So I have 12 minus 6 is 6. So that tells us that out of the 12 volts given by the battery, 6 volts are lost here and 6 volts are lost here. So we have 6 volts lost across a 3 Henry inductor. So we have L di dt equals 6. L is 3, divide over. I get di over dt is 2 amperes per second. All right, looks like we have time for one last question. Well, I guess we'll just finish off this example circuit. So here now, a long time afterward, what is the current through the battery? And stop. Okay, 2 amps, which is correct. So a long time afterward, we know that there aren't any sudden changes. So everything will be steady. There's no di over dt. And so there'll be a steady, I mean, the inductor will just act like a plain wire. So since it acts like a plain wire, it's going to short circuit this 6 ohm resistor here. So the current will flow like this, only through this outer loop. And so we have 12 volts and 6 ohms, so 2 amps is the current. Last question is, we reopen the switch, what is the current through the inductor at that moment? And we'll end after this. Okay, cool. So, all right, overwhelming for 2 amps, which is correct, because remember, with the inductor, the thing is it doesn't want the current running through it to change. And so we know that when the switch had been closed for a long time, there were 2 amps of current running around like this. And so once the switch is reopened, the inductor wants to keep 2 amps running. So to keep 2 amps running, and now it will go like this instead. All right, that is it for today. And we'll talk about LC circuits and ROC circuits on Wednesday. One quick announcement. As usual, for midterm week, instead of a Monday help session, we'll have Tuesday and Wednesday help sessions instead by the CAs. Yeah, probably the usual time, 7 to 9 p.m. I'll let you know if there are any other things. Just a couple of questions to answer. So why doesn't it always just act like a plain wire? Because remember that it's loops of wire that can see a magnetic field. And so if that magnetic field is changing, it will feel an induced EMF. So that hopefully answers Harrison's question. And then there was another question, won't the current go counterclockwise after the switch is reopened? No, so the idea is that, again, remember the thing about the inductor is that it just keeps the current going the same way as it was before. So if the current was running through it previously like this, then once the switch is reopened, the current through the inductor has to stay the same in both direction and magnitude, at least for a moment. And so it will run like this.
Professor,
Mhm.
I was looking for the homework 6 solutions, and when I tried to open them, it was just the homework again. There weren't any solutions in the file.
Oh, okay. Might have been a mistake on my side. I'll upload them again. Thanks
Okay,
for telling.
thank you.
All right, that's all. Thanks for everyone. And I mean, stick around if you have questions, but otherwise, have a good day.
Professor,
Mhm.
I had a quick question. Where I'm right now, there are like 70-mile-per-hour winds, so like my internet was not working for like the first 5 minminutes of class. So could you just go over what you went over there?
For the transformer bit. Okay. Yeah, sure, I can do that. I'll also be
Thank you.
posting a recording, just so you know.
Okay, yeah, I was just in case, like, it's supposed to like keep up all day, so I'm not like sure
Sure that
whether
you'll
I'll
be
have
able to.
internet
Right,
today. Yeah.
absolutely. That's fine. All right. So,
Thank you.
all right. So the idea with so first of all, just a recap of the structure. Okay, let me stop the share and focus on the notebook. Yes. Okay. So the idea is that for transformer, we have a primary coil. It's wrapped around a transformer core, which is basically just a material that magnetic field lines like to travel through. And then there's a secondary coil wrapped around the other arm of the transformer core. This is the symbol for an AC voltage source, is just a sine wave inside a circle. And here we have some resistor, which we call the load over here. So this kind of arrangement where we have two physically separate coils that are interacting with each other because of changing flux, this type of interaction is called mutual inductance.
Okay.
Mutual because, sure, this has current running through it, which creates a magnetic field, which creates a changing flux seen by this. But once this has a current running through it, then that influences back the primary coil again. So they both influence each other.
Okay.
All right. So Faraday's law tells us that EMF is negative rate of change of magnetic flux, but this is the total magnetic flux seen by the coil. Now, what do I mean by total? Is that if you have n turns, for example, then it's the flux seen by one turn times the number of turns.
Okay.
Right? Because basically by including more turns, right, you have effectively increased the area that is seeing a magnetic flux. So might as well do it for a single turn and then times n. So we can set up for the secondary coil, we can set up a relation, the secondary coil's voltage is equal to minus ns times d phi dt, where this is for a single turn. And we can do the same for the primary.
Okay.
But if we look at what's going on here, like the flux seen by a single turn on this side is the flux seen by a single turn on this side.
Okay.
So we can solve for d phi over dt. So that would just be the voltage on the secondary divided by the number of turns on the secondary. And same thing over here, it'd be voltage over the primary divided by the number of turns on the primary. And so that allows us to set up this equality. Vs over ns is equal to Vp over Np, which we can rearrange then to Vs over Vp equals Ns over Np.
Okay. Yeah, that's just about where I was able to join in. So
Okay.
thank you.
Yep, you're welcome.
All right, thanks. Bye.
Bye. Good luck.
Thanks.
Hey, Jing Jing.
Hi, I was honestly just listening in because I also missed like the first like 2 minutes of class.
That's fine.
I was just listening, but yeah.
Okay. Any other questions I can help with?
Nope. Oh, also, is the thing that we started on Friday where we say hello in the chat, is that every class now?
It's going to be every class now, yeah.
Oh, oops. Okay, I can do that now.
Yeah, go ahead, do that now. Yeah, that's fine.
Oh no, wait. Okay. All right. That's all I had. Thank you.
All right. Bye.
Bye. Bye. Thank you.
Mhm.